The sea was a monster that night. Waves crashed against the ship, a fury that seemed personal. Captain Elias stood at the helm, his face grim, watching the horizon just vanish behind these towering walls of water. The wind howled through the rigging, sails groaned under the strain. But what truly gnawed at him wasn't the storm itself, it was the broken steering oar, just a useless splinter of wood. Without it, his vessel was, well, a leaf in the wind, helpless against the currents, destined for jagged rocks. His desperate shout echoed through the chaos. "Rickajury rudder, use the spare spar and lash it to the stern." And in that moment of crisis, you really see the primal human reliance on this seemingly simple, brilliant invention. A tool that saved countless souls over the centuries. And that's precisely what we're diving into today, the unsung hero, the rudder. Because it's not just about boats, is it?
Oh, absolutely not. While our minds instantly picture a boat rudder, maybe on a sailboat or a big ship, there's another equally critical rudder, the one that guides us through the vastly different medium of air. This isn't really a single story of invention. It's more, as we've discovered, a fascinating tale of two rudders. Each evolved in response to fundamentally different physical environments, and, well, they serve profoundly different purposes.
Right. And that's the heart of our mission in this deep dive, to unpack the rich, surprising history, the often misunderstood physics, and the ultimate divergence of these two pivotal steering mechanisms. We're going to reveal how human ingenuity continually adapted to the unyielding laws of fluid dynamics. So get ready to have your understanding of control surfaces maybe completely reshaped. The rudder on water, a millennia-long journey of mastery. Okay, so let's cast our minds back, way back. Humanity's earliest ventures onto water. Think raft, canoes, those frail reed boats we see in ancient depictions. How on earth did our ancestors steer them?
Well, it started with the absolute basics, simple paddles.
Yeah.
Just pushing or pulling against the water on one side or the other.
A lot of effort for very little control, I imagine.
Exactly. Very rudimentary. But that laid the groundwork. The first major refinement came pretty early, actually. As far back as 3100 BC, in ancient Egypt, we see the evolution to the dedicated steering oar.
Yeah.
And these weren't just repurposed paddles, they were massive, specialized instruments, often tied to the side or the back of the vessel.
Wow, massive.
Yeah, some early Egyptian river vessels, the big ones, could use as many as 5 of these powerful steering oars just to try and gain some control. It demanded incredible strength and skill, a real blend of raw power and nuanced know-how. It's like Homer describes Odysseus in the Odyssey, who sat and guided the ship with the steering oar skillfully.
5 oars. That's a lot of muscle needed.
Yeah.
So what came next? Was there a moment where someone thought, there has to be a better way than wrestling multiple giant oars?
Precisely. The breakthrough, remarkably, came during Egypt's 5th dynasty, the tiller. What's fascinating here is how the tiller, initially just a small pin or maybe a handle inserted into the steering oar, provided crucial mechanical advantage. Suddenly, one person could exert far greater turning force with less effort.
Leverage. Makes sense.
Exactly.
Yeah.
Leverage. This led directly to the quarter rudder, which was basically a steering oar mounted on the ship's side near the stern, but now with that helpful tiller. It proved incredibly successful. Adopted by ancient Greeks and Romans, they often used them in pairs, one on each side, and later by the Vikings, they used a single, really robust one on the right side of their longships.
And that's where starboard comes from, right? The steerboard side.
That's the origin, yeah. Starboard. Its remarkable longevity, over 2 millennia, wasn't stagnation. It was adaptive genius. It was the perfectly suited solution for its time, for those kinds of ships. B, a technological crisis, and the stern post revolution.
But even a perfect solution eventually hits its limits, doesn't it? As shipbuilding evolved, especially in medieval northern Europe, they started producing these larger, bulkier cargo ships, things like the cog. And that trusty quarter rudder, well, it ran into a wall, physically speaking.
It really did. It became exceptionally long and heavy, just unwieldy, and it placed enormous strain on its connection point to the hull, a real technological crisis, as you put it. The quarter rudder was literally getting too big for its britches.
So something had to change.
Absolutely. And the stern-mounted rudder became the revolutionary answer. But what's truly astonishing, and this is where it gets really interesting, is its complex dual origins across the globe. It wasn't a single invention popping up in one place.
Dual origins. Okay, so where do we trace its earliest known appearance then?
For that, we need to transport ourselves to ancient China. The stern-mounted rudder first appeared there, incredibly, in the 1st century AD during the Han Dynasty. We have archaeological evidence, like a detailed pottery model of a junk found in Guangzhou, that confirms its early adoption.
And was it the same kind of design we think of today?
Not quite. The Chinese design was incredibly sophisticated and unique for its time. Unlike its later European counterpart, it was suspended by ropes and tackle. This meant it could be raised or lowered. Think about how crucial that is for junks navigating shallow rivers or tricky coastal waters.
That's clever. Really practical.
And even more ingeniously, they were often fenestrated, which just means bored with holes. This reduced the water pressure pushing against the rudder, making it easier for the helmsman to turn. This whole system allowed them to build genuine giants, junks that stretched over 400 feet, enabling Admiral Zheng his grand voyages in the 15th century, just massive ships.
Incredible foresight and design. Meanwhile, halfway across the world, back in northern Europe around the 12th and 13th centuries, a different solution for those big cogs was emerging.
Right. The Europeans were facing the same problems steering bigger ships, but they came up with a different answer based on their materials and ship design. Their innovation was the pintle and gudgeon system. You can basically think of it as a hinge for the sea. Metal pins, called pintles, were fixed to the rudder, and they fit into corresponding brackets, the gudgeons, which were bolted firmly to the ship's straight stern post.
Okay, so a really strong mechanical connection.
Incredibly strong and durable, exactly what was needed to withstand the immense forces on large sailing vessels, especially in rough North Atlantic seas.
And this, of course, raises that fascinating historical puzzle. Was the European rudder an independent invention, or did the idea somehow travel the Silk Road, maybe from China?
Well, the profound mechanical differences really strongly suggest parallel evolution. The Chinese design, suspended, fenestrated, used on ships, often without a strong stern post, is just fundamentally different from the European hinged rudder, which absolutely required that strong stern post. This casts significant doubt on a simple technological transfer. It looks much more like two unique solutions developed independently using available materials, lots of iron in Europe, and existing ship designs, like the cog, to solve the very similar problem of steering larger vessels.
Two different paths to the same goal. Amazing.
It's a powerful example of human ingenuity tackling the same challenge in different contexts. Sea control, exploration, and modern maritime advancements.
So the sternpost rudder, especially the European version, really unlocked new potential. But it wasn't just the rudder in isolation, was it? It was part of a bigger picture.
Exactly. Its effectiveness was magnified by concurrent changes in hull design. Ships got deeper, more stable hulls, and big advancements in rigging. All these things came together. This combination resulted in the full-rigged ship of the 15th century, vessels with unprecedented maneuverability. This is what really allowed explorers like Columbus and Magellan to navigate vast oceans and, change the map of the world.
But these new rudders were big and heavy. How did they actually control them from the deck?
That became the next challenge. The simple tiller, attached directly to the rudder head, got buried deep within the hull as ships grew taller. So they came up with awkward solutions, like the whipstaff, basically a long vertical lever poking up through the decks. But it only offered limited movement, kind of clumsy.
Doesn't sound very precise.
Not at all. The real final breakthrough came in the early 18th century with the invention of the ship's wheel. Using ropes and pulleys, it provided significant mechanical advantage. Suddenly, one or two helmsmen could control even the largest rudders with relative ease and precision. That system was so good, it remained the standard for centuries.
Okay, let's get down to the physics for a second. When Captain Elias turns that jury rudder, or when a modern ship turns its rudder, what's actually happening in the water?
Well, water is dense, right? It's technically an incompressible fluid, unlike air. A boat rudder acts as a hydrofoil. Think of it like an airplane wing, but operating in water. When you turn it, it deflects that flow of water. This creates unequal pressures on its two sides. More pressure on one side, less on the other.
And that pressure difference creates a force.
Precisely. It generates lift, which is the sideways force that pushes the stern of the boat, causing it to pivot or turn. It also creates drag, which is resistance slowing the boat down. And just like a wing, if you turn the rudder too sharply, it stalls. The flow separates, it loses its effectiveness, and you don't get much turning force.
Right, the stall angle. And you mentioned something about propellers.
Ah, yes, the prop wash effect. Placing a rudder directly behind a propeller means it operates in the accelerated water pushed back by the prop. This dramatically enhances its effectiveness, especially at low speeds. You can get significant turning force even when the boat itself isn't moving very fast.
That's a neat trick.
Very useful. We also saw the development of the balanced rudder design, where a small portion of the blade area is placed forward of the pivot point, the stock. This helps balance the water pressure and reduces the effort needed to turn it. And today, modern maritime rudders have gone even further. High-lift designs like flap rudders, which work a bit like flaps on an airplane wing, and even integrated steerable propulsion units like azipods, essentially propellers that can rotate 360 degrees.
Azipods, right. Those give ships incredible maneuverability, almost letting them spin in place.
Exactly. Modern rudders are really high-tech wonders now. They use powerful hydraulics like power steering in your car, but much bigger advanced composite materials for strength and lightness, and they're fully integrated with complex computer systems for navigation and even autonomous control. Some researchers, like Dr. Maria Sanchez, are even envisioning rudders that could flex like a fish's tail for even greater efficiency. It's a continuous evolution, always pushing the boundaries. 2. The rudder in the air. A rapid ascent and divergent purpose.
Okay, now let's pivot dramatically, up into the air.
Right.
Because here, the story is, well, completely different. It's such a stark contrast to the maritime world. The airplane rudder's development wasn't a slow, millennia-long evolution. It was a frantic sprint, compressed into just a few crucial years.
That's absolutely right. A sprint is a good word for it. And interestingly, the concept was initially just borrowed straight from the sea. Sir George Cayley, a brilliant English pioneer in the early 1800s, sketched ideas for flying machines. His designs included a tail unit for control, and part of that was a vertical surface to control yaw, what he basically conceived of as an airplane rudder. It was a direct conceptual transfer from boats, a natural analogy to make at the time.
So they thought it would work the same way, just turn the rudder and the airplane turns.
For decades, that was the prevailing but ultimately mistaken assumption. Early aviation pioneers thought an airplane rudder would function just like a boat rudder, as the primary steering device. You kick the tail, the plane turns. You see this in early attempts by aviators like Henry Farman. His aircraft steered, but in a really sluggish, difficult manner. It was more of a clumsy skid through the air than a proper controlled turn.
Why didn't it work like that?
It fundamentally misunderstood the physics of flight. Air is just vastly different from water. It's about 800 times less dense. So what works for a boat, where you can use the rudder's force against dense water to pivot the entire heavy vessel, simply doesn't translate directly to the delicate balance of aerodynamic forces acting on an airplane in thin air. It needed a different approach. B, the Wright brothers' genius, and the discovery of adverse yaw.
And the critical departure from that old thinking came from, well, two bicycle mechanics from Dayton, Ohio, Wilbur and Orville Wright. Their genius, it seems, lay partly in their unique philosophy of control. They believed an aircraft, much like a bicycle, could be inherently unstable but still masterfully controlled if you had the right inputs. Their focus was firmly on achieving three-axis control.
That's spot on. Control was everything to them. Their early gliders, tested down at Kitty Hawk in 1900 and 1901, already featured wing warping for roll control, twisting the wings to bank. But crucially, initially, those gliders had no vertical rudder. They actually thought banking alone, using the wing warping, would be sufficient to make the glider turn.
An omission that turned out to be key, right, because it led to problems.
Big problems. It led to their profound frustration in the autumn of 1901 with their second glider. When they tried to make a turn by warping the wings to bank, the machine would perversely begin to slide sideways and pivot its nose away from the direction they wanted to turn. They called this frightening phenomenon well digging, because often it ended with a wingtip literally digging into the sand. This was adverse yaw in action, and they just couldn't figure out why their glider refused to turn properly.
So the glider was fighting them, essentially, trying to turn left, but the nose swings right. Why? What was causing that?
It's down to some subtle physics. When they warped the wings to bank, the wing on the outside of the turn, the one lifting more, had a higher angle of attack. This generated not just more lift, but also significantly more induced drag. Think of it like that outer wing was suddenly hitting more air resistance. This extra drag pulled the nose of the aircraft away from the intended turn. It's a counterintuitive force.
Okay, so they identify the problem. How did they try to fix it at first?
Their first attempt at a solution in 1902 was logical but wrong. They added a fixed twin-vane vertical tail, thinking it would resist that unwanted yaw. But it actually made things worse. It exacerbated the problem, making the glider, in their words, absolutely dangerous.
Wow, so back to the drawing board. What was the breakthrough?
The monumental breakthrough reportedly came during a sleepless night, or maybe just intense discussion. Orville had the idea to make the rudder movable, but it was Wilbur who added the crucial, absolute game-changing insight. link the rudder's controls directly to the wing warping mechanism. They achieved this mechanically via the pilot's hip cradle. When the pilot shifted their hips to warp the wings, it would simultaneously move the rudder.
Coordination. And this was the profound realization, wasn't it? The movable, coordinated rudder wasn't there to initiate the turn by kicking the tail around, like the old boat analogy suggested.
Exactly. Its primary purpose was to coordinate the turn, to apply just enough corrective force to counteract that adverse yaw generated by the wings, keeping the aircraft's nose perfectly aligned with the flight path through the turn. It transformed the uncontrollable well digger into a beautifully controlled flying machine. The result was immediate and total success.
So the 1902 glider became the world's first aircraft with true, effective three-axis control. Pitch managed by the forward elevator, roll by wing warping, and now yaw perfectly coordinated by the movable rudder.
That's it, the foundation of modern flight control. They even use a simple yaw string, literally a piece of yarn taped to the front structure, as their first flight instrument to visually confirm this coordination. If the string blew straight back, the turn was coordinated. Genius born from necessity. See aerodynamics and modern aeronautical applications.
Okay, so we understand its coordinated role. How does the airplane rudder actually function in aerodynamic terms, in this thin, compressible air? It's about precision, not brute force, as you said.
Precisely. The rudder, when deflected, creates a sideways aerodynamic force on the tail. This generates a yawing moment around the aircraft's vertical axis, causing the nose to pivot left or right. It serves two principal functions in modern aircraft. Firstly, and this is its primary job during maneuvering, it's about counteracting adverse yaw. When a pilot uses ailerons to roll into a turn, the rudder generates just the right amount of corrective yaw to precisely cancel out that inherent adverse yaw from the ailerons. This ensures a coordinated turn, avoiding inefficient slips where the tail lags or skids where the tail slides out too much, keeps the flight smooth and efficient.
Okay, countering adverse yaw. What's the second main function?
Its second role is directional control and stability, especially when not actively turning. While the fixed vertical stabilizer part of the tail provides passive stability, like a weather vane keeping the plane aligned with the relative wind, the movable rudder allows the pilot to actively control yaw. This is absolutely critical during takeoff and landing, especially in crosswinds. The pilot uses the rudder to keep the aircraft aligned with the runway, even if the wind is pushing it sideways. It's also crucial for maintaining control in multi-engine aircraft if one engine fails. The rudder counteracts the asymmetric thrust.
And even though modern aircraft have designed features like differential ailerons, where one aileron moves more than the other, or freeze-type ailerons, which create their own drag to help counter adverse yaw,
Reducing the pilot's workload, yes.
active rudder control still remains the definitive tool for that precise coordination, doesn't it?
Absolutely, it's indispensable. And in modern jets, we see sophisticated systems built upon this. Yaw dampers in airliners automatically make tiny rudder adjustments to counteract oscillations and give passengers a smooth ride. Fly-by-wire systems automatically blend rudder inputs with aileron and elevator commands for optimal handling. But pilots still actively use the rudder pedals manually, especially for those critical phases like crosswind landings. It remains a fundamental control surface, a testament to the right's discovery, working constantly, often subtly, behind the scenes. 3. Synthesis and conclusion. A tale of profound divergence.
Okay, let's bring this all together for you listening. It's clear that although they share a name and maybe a very distant conceptual ancestor, the boat rudder and the airplane rudder are fundamentally different technologies. It really is like two branches that started from the same root but grew in completely separate directions, shaped by their environments.
It's a perfect example of profound divergence based on physics. Let's systematically compare these differences just to nail it down. First, their primary function. The boat rudder is the primary initiator of a turn. It directly forces the vessel to pivot. But the airplane rudder is primarily a coordinator of a turn. It refines a turn that's actually initiated by banking the wings with the ailerons. Remember the saying, the rudder does not cause the turn, it refines a turn caused by the wings. Big difference.
Okay, function first. What else?
Second, the fluid dynamics. We touched on this. Water is roughly 800 times denser than air. This means relatively small boat rudders can generate immense forces, but the response tends to be slower. Airplane rudders operating in thin air need to be much larger relative to the aircraft's size to generate meaningful forces, but they allow for quicker, more precise adjustments. It's a whole different feel.
Dense water versus thin air. Got it.
Right. Third, their control philosophy. A boat executes what's essentially a flat turn. It skids across the water surface, pivoted by the rudder's side force. An airplane, however, executes a banked turn. It uses the horizontal component of the lift generated by the banked wings to pull itself through the turn. The airplane rudder's role is entirely subordinate to this banking process. It's there purely to ensure the turn is smooth, efficient, and coordinated. The boat rudder is the engine of the turn. The airplane rudder is more like the fine-tuning system.
Completely different ways of changing direction.
Completely. And finally, number 4, their developmental trajectory just diverged entirely. Boat rudder evolution focused on strength, mechanical advantage, and hydrodynamic efficiency in water. We saw the pintle and gudger, the ship's wheel. It was all about applying brute force more effectively against dense water. Airplane rudder evolution, on the other hand, focused entirely on integration, coordination, and solving unique aerodynamic puzzles like adverse yaw. Its development was inextricably linked to the ailerons and the whole concept of three-axis control. They evolved along entirely separate tracks to solve distinct engineering challenges posed by water versus air. Outro.
It's really an incredible journey when you lay it out like that, isn't it? From a simple paddle battling a furious storm, maybe like Captain Elias faced, to today's high-tech integrated systems on giant ships and soaring airliners. It truly emphasizes the sheer human ingenuity, that persistence, and the adaptability required to understand and then master the powerful and very different forces of both water and air.
Absolutely. The story of these two rudders is such a powerful example. It shows how a single, simple idea, steering, when placed into two radically different physical worlds, gets fundamentally reshaped by the immutable laws of physics governing those worlds. You end up with entirely distinct, purpose-built solutions. It's engineering's elegant response, you could say, to the problems posed by the natural world.
So, the next time you see a rudder, whether it's on a tiny kayak paddling down a quiet river, a massive container ship navigating the ocean, or you glimpse the tail of an airliner as it cuts through the clouds, I hope you look at it differently. Maybe appreciate the hidden history, the centuries or the frantic years of innovation, and the profound physics behind these essential instruments of control. And perhaps that appreciation might just spark a desire to explore even more deeply. Maybe into the fascinating world of fluid dynamics itself, or perhaps digging into the specific historical periods of maritime or aeronautical innovation we touched on. Thank you for joining us on this deep dive.